Okay, well, we've got a number of people that have joined, so we might start. So welcome to the machine learning and astronomy meetings. So if we just quickly go around and say a quick word, who we are, where we're from, what we're interested in. I'm Kieran, I run them. I'm a PhD student over at Western Sydney Uni, trying to work out redshifts using machine learning. Carl, are you there?
Yeah, Carl Blanchard from Swinburne. Yeah, do quite a bit of machine learning and astronomy. Do research on very high redshift galaxies mostly.
Awesome, thank you. Ray?
Ray Norris. I'm at CSIRO at Western Sydney Uni, and I mainly work on the EMU project.
Awesome. Clara?
I'm Clara Pennock from Keele University. I mainly use machine learning to classify AGN behind the Magellanic Clouds.
Awesome, thank you. Rosalind?
I'm Rosalind Wong. I'm from WSU and CSRO. I'm a machine learning research scientist.
Awesome, thank you. Julian?
Hi, I'm Julian. I'm a PhD student at the Max Planck Institute in Garching of extraterrestrial physics. I'm interested in high redshift QSOs mainly, and I'm working on Rosita data. I'm using machine learning to identify counterparts for X-ray sources.
Awesome, thank you. Ken?
Hi, Ken Duncan, University of Edinburgh now. I produce most of the redshifts for the LOFAR surveys, and I'm also the Deputy Science Team Lead for the WEAV LOFAR spectroscopic survey.
Awesome, thank you. Mattia?
Yep, I'm Mattia. I'm at UWC/IDEA in Cape Town, and I dabble in machine learning. I'm into identify and classify sources in multi-wavelength surveys, originally infrared and now increasingly optical radio.
Awesome, thank you. Kai?
Yeah, hi, I'm Kai. I'm from the Heidelberg Institute for Theoretical Studies. I'm head of the astroinformatics group there, and I do a lot of applied machine learning in astronomy and astrophysics.
Awesome, thank you. Shingo?
Hi, I'm Shingo. I'm a PhD student at Swinburne, and I'm working under Carl, and my project is aimed at finding high redshift objects using machine learning techniques.
Awesome, thank you. So we just have our speaker, Antonio, left. Antonio, did you want to give a short bio and take it away?
Yeah, sure. So yeah, I'm Antonio Dicento. I'm a postdoc at the Heidelberg Institute for Theoretical Studies in Kai's group. And at the moment I am working in the ESCAPE project, so building platforms and infrastructures for astronomical data.
Awesome, thank you. Did you want to start presenting?
Sure. I will just share my screen. Just a sec, probably I have to move these windows up. Sure. Okay, do you see my presentation?
Yep.
Okay, let me go to full presentation mode. Okay.
Awesome.
All correct?
Yep.
Okay, so many thanks for the opportunity of giving this presentation today. And in this talk, I will basically give an overview of what has been my PhD thesis project. That was about photometric redshift estimation using machine learning. And in particular, I will present two different models, two different methods to estimate photometric redshift. One that is fully automatic, based on deep learning, and the other one that is feature-based. So this is something that is probably well known to all of you, but let me give this quick introduction about redshift. That is a fundamental measure of distance in astronomy, and it is defined as the shift of the spectral lines toward the red due to the expansion of the universe. And for its own definition, it's measured using spectroscopy. but getting spectra is a complicated and expensive, time-consuming task. So it's not always possible to get all the spectra for all the sources that we have available and that we need. And then a solution to this problem is using instead photometric redshift. So obtained not from spectra, but using photometry based on broadband imaging. And this allows us to obtain the distances for all the sources required. And there are two big families of methods in order to obtain photometric redshift. One is template fitting, and the other is empirical methods. And in particular, machine learning methods, on which I will focus during this talk, is a subfamily of empirical methods. So, in general, in the literature, if you want to perform photometric redshift estimation, you should follow this pipeline that I'm showing here, in which you start from the images. You somehow to extract some photometric feature that could be, for example, magnitudes or colors. You have to select the features that are more appropriate for the task, and then apply a particular model, and then use it to deliver the prediction, the estimation of the redshift. And in our work, we had some focuses on which we wanted to put our attention in the process of photometric redshift estimation. That is to say, the feature extraction and selection, in the sense that we wanted to understand if it's possible to improve what is done in the literature about the classic features that are normally used. There was a topic of point estimates versus PDFs, so the way in which the photometric redshifts are, the form in which photometric redshifts are estimated. Of course, you can understand clearly that probability density function gives more, brings more information with it. It gives the possibility to associate an error to the prediction. And connected to this aspect, there is also the topic of how to correctly evaluate the error in the case of the prediction of a density function. Then there is the aspect of taking into account multimodalities, because the redshift problem is a degenerate problem. And so we needed to find a way to consider this aspect. How to use all the available information in a way that is as best as possible, and how to improve in general the performance of the predictions. With these points in mind, we built two different models, two alternative models. The first one, as I said at the beginning, was an automatic model based on deep learning that was automatically extracting and selecting the best features, taking images there directly as input, putting them into the model, and then giving the prediction. So it skips completely the two steps of feature extraction and feature selection, because they are automatically addressed by the model. The second model instead was based on a manual feature extraction performed in a massive way, and then combining this feature and applying a greedy forward selection algorithm to select the best features for the model, and then giving the final prediction. Now, let's start to give a look to the first model. The first model, as I said, was a deep learning model based on the combination of a convolutional neural network and a mixed density network. And for this reason, we called it DCMDN, Deep Convolutional Mixed Density Network. This model had the advantage that it could take images directly as input, and thanks to the convolutional part, it could extract automatically those that are called feature maps in order to predict and select automatically features in the end that will become the input of the second part, the mixed density network part. That is a fully connected neural network able to predict the parameters of a Gaussian mixture model, so the means, the variances, and the sigmas. And doing this, we were able to predict, to estimate photometric redshifts in the form of a Gaussian mixture model, so of a density distribution. And yeah, so I tried to explain the relation between the different layers in the mathematical relation in the bottom, so you can see that the final outcome is a Gaussian mixture model. And at this point, there's an important consideration that we needed to do, because when dealing with PDFs, we need to correctly estimate the error between a distribution and a point estimate, that is the true redshift, the spectroscopic redshift that we use it to train the model. And typically in the literature, we found that this was done using a measure like the root mean square error and taking its mean. But in our opinion, this was wrong, and or at least not the best thing to do, because you are giving up all the information that is brought by a PDF, and also there's a possibility to occur into misleading results. And if you will give a look at my thesis, there is an entire chapter dedicated to this aspect. But for now, I just want to say that we introduced this, for the first time in astronomy, this measure, the continuous rank probability score, the CRPS, that is exactly meant to deal with this problem, estimating the error between a distribution, a density distribution, and a point estimate. And it is done using this relation. Probably I should move a bit this window. Okay. It is done using this relation. So the two functions are transferred into their cumulative distribution function. And what we do is basically calculating the area between the step function in which the point estimate is transformed and the CDF of the predicted PDF. It's clear that the smaller that area is, the smaller will be the error. And we use it, the CRPS, not just as a score function, but also as a loss function to train the model. The second tool that we adopted is a visual tool, a quality tool to check the quality of our distribution, of our predictions. And it's called PIT, probability integral transfer. It is estimated taking the CDF of every predicted PDF and evaluating it at the point of the spectroscopic redshift, of the true redshift, and then drawing an histogram. Now, in the ideal case, this histogram will be flat, and then it's telling us that in mean, the distributions that we are producing are well calibrated, to use the correct term. So their shape is correct, more or less correct. But then we can have the case of over dispersion when the distribution is peaked in the center. And this is telling us that our distributions are typically too broad. And then this is not, you can imagine that this is clearly not a good prediction, because if the distributions are always too broad, perhaps the true value will fall inside the distribution, but it will be maybe in the tail, and then we are not predicting well. In the other case, instead, that you can see on the right histogram, we speak of under dispersion, when the histogram is U-shaped. And this happens when the predicted distributions are too narrow. And then there's a high probability that the spectroscopic redshift will fall outside the distribution. So both are indicating problems in the training and prediction phase. So now let me show you some results that we obtained with this model. And these are relative to a quasar catalog taken from the Sloan Digital Sky Survey. We used IPS to collect the images. And I'm comparing the results of the DCMDN with two classic models, a random forest and a standalone mixture density network trained using features, classic features. And in the main plot, also on every vertical, on every y-axis, there is the sum of the distributions falling onto that axis. So you can clearly see that the PIT results are more or less good for all the three models, but the CRPS value is really improving a lot. and also the plots are the plot in the case of the DCMDN is cleaner and this with respect to the other two models, and this means that also the amount of outliers is kind of reduced. But even more interesting is this second experiment in which we used the mixed catalog, combining quasar, galaxies data, and also stars used as contaminants, and of course they had a redshift 0. And this is going toward the direction of a more real case of application. And it's clear from the plots that in the case of the random forest and the mixed density network, they fail completely because the PIT histogram is completely off, probably because they can't deal with the presence of the SARS. And in fact, in general, when dealing with these kind of problems, one should pre-classify the data. This is not true in the case of the DCMDN, in which the PIT is still showing some problems. It's not perfect, but still the model is able to give a result that is kind of more reasonable. And also the results obtained with the CRPS shows that it's much better with respect to the other two models. So let's keep this in mind for the moment. And let's see instead the second model that we built, the one based on features. What drove us in building this model was the fact that the DCMDN has also some weaknesses, some weak points. In particular, the fact that as every model based on deep learning, it tends to become a black box in the sense that it's really hard to give a meaning, a physical meaning to the features that are automatically produced by the model itself. And then we say, okay, let's consider the classic 10 features that are used in literature, that is to say the colors, using PSF magnitudes and model magnitudes, and the two magnitudes in the R band for PSF and model mag. And let's say, is it possible to combine the power of the machine with the expertise and the knowledge that humans have when doing feature engineering? And so what we did was taking all the 90 parameters available from the Sloan Digital Sky Survey database, photometric parameters, and also shape-related parameters, so magnitudes, errors, radii, ellipticities, and so on, and doing a massive combinations of these parameters in differences, pairs, ratios, including the reddening, and so on. And we ended up in this way with a number of 4,520 features. Now, if we want to do all the possible combinations in order to obtain subsets of 10 features, we will end up in a number that is closer to 10 to the 30 sets of features. And in order to find the best set, the best performing set of these features, we should do 10 to the 30 experiments. And this is clearly not manageable, not a clever strategy. We need something better. And our solution was applying a forward selection. So the forward selection is a procedure that is explained in this diagram, or in the complicated relation that I wrote on the bottom, in which we were doing, we were taking randomly 100 subsets for training and testing from the data, and doing recursive experiments using the KNN, always selecting the best features and then blocking them and repeating the experiments, adding a second features, a third features, building a tree of possible best features in which every branch, stopping at 10, was a best 10 feature candidate. This operation required an intense use of GPU computing, because you had to do every time 100 sample, testing 4,500 features plus 4,520 features plus including cross-validation. But then at the end, when we had built our tree of features, we tested all the branches, all the independent branches with an independent model, the random forest. in order to verify which one was the best performing one. And we use this diagram, the core diagram, to visualize the complex structure of the tree of features with all the relations and the connection between the different features. It is a bit complicated at the beginning. I needed something like 2 months to fully understand it, but if you spend some minutes on it, it will be already clearer. And it's really a powerful instrument to visualize such a complex structure. But what I would like to put a focus on is the fact that on the left side, you can see the list of all the features that we produced appearing in the tree. So it's not just the best set, it's all the features. And you can see that these features also look kind of weird. They are not immediately interpretable. What is it, for example, I don't know, something like R-petro divided RPSF or RPSF divided GXP? I can't say, but the interesting thing, and I will come back on this in a few minutes, is that we managed to give a meaning, physical interpretation, at least to some of these features. And this is the interesting aspect, the very interesting aspect of this work. But for now, let's give a look to the results. And so here you can see the usual plots that are always used of true redshift versus estimated redshift. In the case of the classic features, of just the first 4 in order of importance feature of our best set, the one that we identified with the random forest, all the 10 best features, and the results given using the DCMDN. And you can see that already from the addition of the fourth best feature, giving also a look at the table, our set is giving already a performance that is comparable to the classic features. And using all the best 10 features, this model outperforms clearly the classic 10 features, but also the DCMDN that is automatically producing something like 65,500 features. So this means that this model is able to really capture the important information and to use it more efficiently than other models. And this is also happening in the case of the CRPS, so predicting our performance with the CRPS. And now let's come back to the aspect of finding a meaning to these features. And we noticed that if we transfer to the redshift space the position of some quasar emission lines, so they're wavelength, and if we calculate the feature importance of some features, those that are composed by, doesn't matter how, but that are composed by filters that are equivalent to those of the classic features. So calculating the feature importance per beam in redshift, as given by the random forest, the peaks of feature importance are perfectly corresponding with some of these emission lines of the quasar. And then this means that this is not always true for the classic features. Sometimes these peaks are just partial, sometimes they do not up at all. So this means that the features are somehow capturing the physical processes that are occurring in the sources. And they are able to transfer this as an information to the model and use it to improve the redshift prediction, the redshift estimation. And this is probably more clear from these other slides, in which I just zoomed on a particular feature. So if we want to compare these models, then both have advantages and disadvantages. The first model, as I said, it's fully automatic, gives a better performance with respect to traditional models used in the literature. It's fully probabilistic and then puts a focus on calibration and sharpness of the predicted PDFs using the CRPS as a loss function, training the model using the CRPS. It takes into account multimodalities, so our predicted PDF shows all the multiple peaks because we use a GMM, a Gaussian mixer model, as a prediction form of the predicted PDFs. It doesn't require pre-classification of the data, but on the other end, it has this problem of becoming a black box, and it's not easy, or at least, yeah, we couldn't give any feature interpretation to any interpretation to the predicted features. On the other end, the second model gives a better performance with respect to the classic features already from the addition of the fourth feature of the best set. It has even a better performance with respect to the DCMDN, and it's possible to give a meaning to these features, or at least to some of them. But it's not really probabilistically calibrated. It's not a probabilistic model, and there's no the best set of 10 features that we are giving is not the absolute best set. It could be that with another model we could find another best set of features. So this is true with this specific model and in this experiment with this data. Oh, sorry. But let me conclude then. These models, anyhow, are quite general. They could be used even and they are used already in different fields. For example, in the weather forecast field, some colleagues of us, from which we took the idea of the CRPS, took it back and used it as a loss function for their neural network models in case of weather forecast. And they are, recently the CRPS has been used also for medical applications as a loss function for a neural network model from, I'm reporting the citation here in the bibliography from Avati and Andrew Wu from Google Research. So eventually this seemed to be a good idea. And also we introduced it for the first time, this new evaluation tool in astronomy, that is to say the CRPS and the PIT. And this is a very important point because if you spend a bit of time thinking of it, using measures like the root mean square error in such a case could really bring to results that are completely wrong, completely off. And we spend a lot of time in convincing colleagues that this was an important topic. And also, it's a work that goes in the direction of preparing new missions that are coming, like Euclid, for example, was success will be highly based on the availability of a lot of photometric redshift. So here I'm, as I said, giving the bibliography with my PhD thesis, the papers in which these two models are presented, and also the other citation is about the weather forecast work I referred to, and the one about medical applications, if you want to give a look to them. So many thanks for your attention. I'm eager to listen to your questions, and I wish you to stay healthy in this weird and troubled times. Thanks.
Thank you very much, Antonio. That was fantastic. Does anyone have any questions? Ken, did you want to start?
Yeah, so a question about the feature selection. So presumably for feature surveys, you almost want to invert this problem and tell the survey what features to produce as part of their catalogs. So can you tell Euclid and LSST these are the best photometric measurements to make to provide photometric redshifts, or do you always have to work from the existing data sets?
No, you have to apply. I'm not sure if I got correctly the question, but you have to apply the model and find the features that are specific for that problem, for that case, for that data set. You can't use these features.
But now, I'll clarify. So now that you've worked it out for SDSS, then you could apply this to other existing surveys. If you see patterns in those features, can you turn around and try and optimize future surveys for them to provide better features?
Oh yeah, okay. Yes, this is now I see. I think I see what. Yeah, yeah. This could be done for sure. Yeah, I think so. I mean, it's not something that we tried, but yeah.
Perhaps a quick answer to that as well. It's can that in principle we take spectra, try to create synthetical photometry out of that, because the question is more
Yeah.
than just tailoring certain features. It's more about designing a perfect instrumentation, talking about what is a good set of filters if you want to do certain tasks. And that's a problem we are working on, to find a nice way of actually inverting the problem to the stage that you can exactly say, those are shapes of filters you should use, given the technicalities
Mhm.
in producing them.
It's somehow what you were trying to do with Kieran, I think, or similar to the work that Kieran was done. I don't remember very well, but yeah, it was a couple of years ago. So
Awesome.
It was a starting point in that direction, sort of, but
yeah,
it was not aiming on that.
Carl, you have your hand up.
Yeah, I was wondering a bit about the second method with the manual feature extraction. So I might have missed this. So you're also using those to train a Gaussian mixture model? So it's the same back end, just a different front end?
No, sorry, I couldn't hear very well. You asked about
Yes.
the second method and the features, but then
The second method, you're doing an importance matching on the features. So then how are you going from the features to the redshift? So you apply a similar mixture density network?
No. So in the first model, we use the Gaussian mixture model to go from the parameters that we predict with the neural network to the density distribution. In the second case, we are mainly working on point estimates. So we use the KNN from the features and we predict point estimates. But there was a way to get somehow a distribution. I know that is probably not 100% correct. But when we use the random forest with the final best set, we can take all the prediction of each tree of the forest in order and use them as the points of a distribution. So to get out to fit a model to that distribution, to fit a distribution to that prediction. So this is why we were giving also the CRPS results, apart the root mean square result, to also in the case of the second model. But mainly the second model is not probabilistic.
Yeah, this quantile regression forest is good for estimating a lot of quantiles of the distribution correctly by using the individual predictions of the trees, but it's not giving a fully calibrated PDF. That's truly a difference.
Okay.
And also you can't train that model using the CRPS. It's just use it as an evaluation tool. But the random forest, we were using the sklearn model. And
Cool. Any other questions? I've got one. So what you mentioned that your mixture density model was improved by including a whole bunch of stars in there. How did you mix those? Did you just get an equal number of stars as quasars, or what?
More or less, because we took all the quasars available for, I think we used year 7 and year 9, so it was around 185,000 quasar, more or less. And then we took 200,000 galaxies and 200,000 stars. Mix all together, define a train set and the test set, throw in.
Okay. Was your model then, so you could, I'm assuming that you could predict the redshift at being 0. Would it then classify as a star being 0, or is there some additional classification there?
No, nothing. I mean, you could use it to also obtain a classification, at least for the stars, because those that for which the predicted redshift is 0, you can say, yeah, okay, this is a star. So in principle, you could use it as a classifier, but no, we didn't add any other information. Just put the redshift of stars at 0 at the beginning. All the others have their spectroscopic detection of the redshift. Those are the labels.
Yeah, in the plot tiering, you actually can see that for higher redshift sources around 2.5, you actually see there is a disambiguity in redshift. So you see it for the MDN, for example, it easily mistakes sources around 3 to have a redshift of 0 and vice versa. And that just tells you that it's not able to do in place the correct classification that is necessary to do the regression correctly, because it's done implicitly or directly by the model itself. And that helps you to discriminate sources. And for those that are high redshift sources, you see there's double peaks appearing. So it could be a source at that redshift or a star, something like that.
Mm-hmm.
Okay. So this was just SDSS? Wasn't any other wavelengths?
Yeah, just SDSS, UGRIZ. And also for the images, of course, we took UGRIZ.
Yep. Would adding other wavelengths help, or would that just confuse it?
No, could. I think it could help to even reduce some degeneracy effects that are somehow already taken into account by the fact that we are using a Gaussian mixture model, but could help. Yeah.
Okay. Which leads to the next question. Do you know how this would handle if you included radio data in it? Given that radio data, the sources aren't always...
That's a very good question. I don't know. It would be worth trying.
Okay. Any other questions?
I think, Kieran, that's probably a nice experiment to start in using images on one hand side, giving you certain morphology or whatever size estimates in place, and putting this in the radio together with some other features from other catalogs could be
building
worth
a
trying.
mixed model with some features automatically extracted and other manually engineered.
So Kieran could be a good idea, actually.
It would be particularly interesting, even if you could include additional information. So if you had a polarization map or anything like that.
Yeah, or spectral index.
Yep. So how much could you put into this before the performance would start to suffer? Or before you need to start to do some feature selection on your images?
You mean how much from the point of view of what?
How many,
training epochs?
How many feature maps could you include?
Oh, okay. So hyperparameters.
At the moment, we're talking about adding, a couple of.
It was not that much. I mean, this is something that we really found empirically, just trying and trying. But it was in the order of some hundreds, if I remember well. We had not really a big model, something like 3 or 4 convolutional layers, each with some hundreds of feature maps, alternated with pooling layers, and then a couple of fully connected layers. That's it. It's not really a big model. In fact, it was running in a couple of hours.
Did that require a GPU, or was that?
Yeah, absolutely. Yeah. Not that a big model, but the data were a lot, and then the number of parameters was a lot. So on CPU, we tried it at the beginning. It was absolutely non-manageable. I have somewhere a table showing the comparison between single core, 8-core CPU, and then several GPUs. It needed 4 hours on a single core 1 hour or so on 8 core, so for one epoch, just one epoch, and a minute or so for each epoch on Titan X or P40 Pascal GPU. So that was the moment in which we had the breakthrough, when we transferred on GPU, and then we started to do experiments, and then you can find the best solutions, the best combination of hyperparameters.
Okay, cool. Any other questions? If there's no other questions, let's thank Antonio again for a fantastic talk.
Many thanks to you.
Thank you for coming along, and we will see people in the next talk in a fortnight, those that can make it in a fortnight.
Okay.
Have a great night.
See you then, and have a good day or good night, depending from the time zone.
See ya.
Bye-bye. Bye.
Bye.
I'm still with the coffee. Great to see you, Kieran.
You too.
Yeah, long time no see. And actually, I think we should